we introduced Palette-PrintAR, an augmented reality design and simulation tool for multicolor resin 3D printing. Our tool allows users to model, simulate, and fabricate fluidic networks for multicolor injection 3D printing. We motivate our approach and illustrate a typical user-designed workflow in this presentation. In HCI, there is increasing interest in using augmented reality to enable interactive fabrication, defined as workflows that involve the user at every step in the making process. This includes techniques allowing users to control robotic manipulators for plastering, as shown to the left, understand linkage mechanisms more intuitively, as shown in the middle, and design CAD with a personal responsive 3D printer, as shown to the right. Palette-PrintAR extends this body of work to resin 3D printing. We are inspired by traditional 2D resin artists who utilize layering, swirling, and marbling to rapidly prototype rich, variegated color textures in their pieces. Our workflow is in large part motivated by the fact that traditional resin artists do not typically utilize 3D printing, for a number of reasons. As Ana Rendic, an Argentinian-American resin artist, explains, quote, "I don't incorporate resin 3D printing in my work because I'll feel I don't have much personal involvement before, during, and after the process, as much as working with molds and pouring the resin and mixing the colors." Rendic here is pointing to a crucial gap in 3D printing currently, a woeful lack of input solicited from the designer during the actual making process. Our 3D fabrication approach is an add-on extension to existing stereolithography-based printers, which we equip with syringes for multicolor injection during printing. In our approach, the build platform connected to the syringe pump constitutes the paintbrush, and the resin vat the palette. Users engage with our interactive fabrication workflow in two phases. In phase 1, after initiating tracking of the real-world printer, as indicated in gray, the user assigns material colors to each of the 4 injection ports on the modified build platform. They can then model fluidic networks, including injection sources along with barriers, to guide fluid flow, which they can simulate in real time in the AR session, adjusting their design accordingly. In phase 2, the user is guided by real-time computer vision analysis, which extracts color contours deposited by this injection scheme. Users can then position CAD models in the situated printer context thereafter, executing multicolor printing, during which different colors in the vat manifest in their final objects, iterating on this workflow to prototype a new fluid distribution. We now illustrate several real-world example user sessions demonstrating our tool. The first step in our workflow is inspired again by the practices of practicing resin artists such as Rendic, who says of her process, quote, "I work intuitively. I'm never sure what color I will set first, or what mold I will use until I set everything in my working table." Hence, in our workflow, the user begins by designing fluidic networks in step 1, with for instance 2 injection channels, as shown to the left, or 3 or 4, as shown to the right. To get immediate feedback on their designs, users can then simulate fluid flows through such networks, and into the vat, in real time using OB Fluid in Unity, either in the full printer context, as shown to the left, or with their vat wherever is convenient, for instance at their desk, as shown to the right. Such distributor networks can then be printed layer by layer in step 3, which comprise hollow channels, each branching from a platform injection port. Users can then employ such conduits to spatioselectively deposit resins in step 4, prototyping unique color distributions in each design session. Every resin combination, geometry assignment, and injection scheme gives rise to a distinct multicolor interface. This color distribution defines the palette onto which users position their CAD models in step 5. Again, this step is deeply inspired by the practices of traditional artists. Rendic points out, quote, "I find my piece within the material. It is very tactile, and I have to be fast too, so the body and mind are very connected. Hence, unlike in traditional external slicing software, our approach allows users to drag, drop, rotate, and reposition their models directly in the real-world printer context, based on observed color interfaces, emulating this practice of traditional resin artists designing with their pieces evolving in front of them. Users can also leverage our real-time computer vision tracking module to more quickly analyze vat color distributions. After initiating tracking, the user can toggle a bird's eye view that extracts and visualizes color contours for the entire vat, or zoom in on 2D regions of interest to analyze their color composition, resizing and repositioning such windows to explore the design space. Our computer vision module also assists users in identifying optimal positions for their CAD models using a custom algorithm that inputs the user's color assignments to identify 3D object positions satisfying those constraints. The resulting CAD model poses, both position and orientation, are visualized both in the user's 3D space and in the overlaid 2D bird's eye view. Choosing only one color positions the user's model within the corresponding color region, or as shown in this case, a two-color selection attaches objects to multicolor intersections. To increase the accessibility of our tool, and drawing again on our computer vision module, in the AR interface, users can adjust visualizations of detected color regions appropriate for common forms of color deficiency. We allow users to toggle between the color deficiencies protanopia and deuteranopia, adjusting our visualizations accordingly, displaying yellow instead of green and pink instead of red colors. Throughout our data visualizations, we include a dynamic 3D model, which also reflects these color schemes and includes predicted color interfaces in the final models. Hatch patterns also ensure color is not the only indication of resin color interfaces. With their positions finalized, the user's models can then be printed in step 6. Multiple colors manifest in their final objects in a manner unique to every print, dictated by the user's design choices made during the interactive fabrication session. Through such multicolor fabrication, we seek to achieve the same complex, variegated properties traditional artists such as Renditch achieve in their work. As Renditch describes, quote, "The layers, inlays, and colors generate different surfaces. The pieces are composed of these combinations, and at the end, when I have the final composition, all the elements together, I have an architecture of forms." We also use our augmented reality tracking functionality to increase the accessibility of multicolor printed objects themselves. Drawing on our platform's markerless AR tracking capabilities, users can view multicolor objects from multiple angles, with color deficiency-friendly 3D model visualizations displayed immediately next to real-world models, such that users gain both from tangible interaction and also benefit from accessible multicolor visualization. A far broader design space than can be summarized in this short video is available to users of Palette-PrintAR. This includes designing and fabricating solid barriers that direct fluid flows emanating from their injection sources, engineering multicolor mixing by tuning resin dye diffusion times, and layering multicolors on top of each other to achieve veining or marbled textures. For more details about Palette-PrintAR, including our fabrication process, simulation strategy, and computer vision implementation, please consult our paper. Thank you.